presentation is quite related to the question. The problem is data is anonymous. So how can we still utilize the anonymous data and identify either the demographic groups or kind of the latent classes of groups so that we can still acknowledge the heterogeneity in behavior of different groups. So this is what I'm going to focus on today. And so just to give a bit of background, assuming that there are some students here in the audience as well. So by big mobility data sources, I'm referring to data sets like GPS, mobile phone data, or smart car data, which usually are anonymous. And for this reason, the majority of application using this data have been limited to like kind of visualization or spatial analysis type of things, where the demographic attributes are maybe not so crucial. But we're living in a time where the transport landscape is rapidly changing. We have all these new sorts of mobility services. Then we're going to get new technologies like self-driving cars and flying taxis soon.
Charisma.
On the other hand, the user groups are changing very rapidly as well. Like we have no, is the slide moving?
Yes,
Hello?
I was going to suggest that it seems we're having trouble with connectivity. If you can maybe turn your video off to improve the voice. Thank you very much.
Yes, so basically the user group is getting very heterogeneous as well. So sometimes like the machine learning type of models, they can predict the similar scenarios very well. But when we are looking at forecasting the travel demand for a very different future, they may not be enough. So that's where actually like where the choice models or econometric models can play a role, because in these choice models, basically, rather than just looking at the current patterns, what we try to do is we try to quantify the heterogeneity among different groups by different sensitivity in different factors, like difference in sensitivity to travel time among different groups, for example, or difference in sensitivity to travel cost among different groups. So, and then we try to predict the choices. So these mathematical models basically establish a relationship between the attributes of the alternatives and socio-demographic characteristics with the choices. And typically these models were developed using survey data where the socio-demographic characteristics were observed. And to make this, looking at using the passive data sources for developing this sort of models, we come across the problem that the data is anonymous, so we do not know the socio-demographic characteristics. So in this presentation, I'm going to talk about two case studies. The first one is where we used a smart card data to capture the differences in sensitivity towards peak spreading policies. So it's a data set from China, where so here we did not have the demographics, but we tried to capture that based on the other attributes of the kind of travel habit of the users. We divided them into classes probabilistically and tried to get some more richer inference. And the second one is where we actually predict the demographics as well. So coming to the first case study, so this the link to the paper is given here. So in this one, the background is in Beijing. There was a pilot pricing strategy for the subway, which is very, very overcrowded, that they wanted to shift people from the peak to the off-peak. And there was a fare reduction offered that if people traveled before 7, they will get a discount, 30% discount. Now, they were interested how this kind of pilot study can be used to find the optimum discount and the optimum kind of cutoff time for peak versus off-peak for different stations and lines. So because it was quite, the stations are quite heterogeneous, we thought that it's not enough just to apply like directly the same proportion of shifts, we need to acknowledge the heterogeneity in the responses. So the data we had was smart. So it had the card ID, the checking time, the origin and the destination stations, and it had about 19,000 unique smart card users. Then there is, first of all, policy to do the analysis. So we could infer whether a person has shifted from off-peak to peak-to-off-peak or not. And we also could calculate their pre-travel, what was the standard deviation of their trip start time, and their kind of number of unique OD pairs they were traveling. So we had these sort of information to classify them into different groups. So our kind of, instead of just using a traditional clustering method, we tested that as well. We found that a probabilistic method where we actually assigned the users probabilistically into different latent classes and use that to acknowledge the heterogeneity in their responses in terms of shifting to off-peak versus peak, that performed better. So our results indicated that the model with 4 latent classes of users performed the best. And these 4 classes had significantly different sensitivity towards monetary savings in terms of fare savings associated with pre-peak travel, and also different sensitivity towards the schedule flexibility, or because if someone, for instance, traveled at 6:50 a.m., he or she did not have to change the time at all. But or if someone traveled at 7:10, they just needed to shift by 10 minutes. But if someone was traveling at 8 a.m., for instance, for him or her, it was a bigger change. So we also try to capture this required change in departure time in order to move to the off-peak. And as I mentioned, so we found that actually among these classes, 2 of the classes were very price sensitive. And the sensitivity to the required changing departure time was very different among the 4 classes as well. So I'm skipping some of the details, but just to summarize the findings, we found that when we have these probabilistic latent classes, the explanatory power of the models was much better, and it was useful for the policymakers because we got better behavior insights that they could use for designing the peak spreading policy in other stations. And right now we are actually working on something which is tied to the second case study, where we are trying to collect some survey data so that we can actually predict the relationship between the latent classes and the sociodemographics as well. So this is more of an ongoing work. So now moving to the second case study. So this was led by a PhD student who worked with me a couple of years back. So he was working with mobile phone data, and in this in this paper, he looked at, can we actually predict the demographic features of the users using what we call reverse discrete choice modeling, so that we can use that in predicting their travel behavior. So the basic framework here was, so we know that the travel behavior is a function of the demographic group and the attributes of the alternatives, like attributes of modes, for example. But this demographic group is unobserved in the mobile phone CDR. But our hypothesis was we tried to predict the demographic group from the other observed variables we had from the CDR data, especially their phone calling patterns, the trip motives, etc. So in our data, we had this was mobile phone data from Switzerland, which was part of the Nokia data challenge. So there was GSM locations, call logs, and demographic information from a subset of the users, 158 users to be precise. So we try in the first predict the demographic group of the users. So this demographic group meant that whether they were young, full-time worker, males versus suppose like old females who are not working, things like that. So we could not pinpoint specific age or specific gender, but we were trying to predict the demographic kind of combination of different demographic factors using their phone calling patterns. So these phone usage variables included like the duration of the phone calls they were making, the timing of the phone calls, whether that was during office hours versus in the evening, then how many unique callers they were using, they were calling, etc. So these type of variables. So from the call detail record data, we had this phone usage variables and we estimated this demographic prediction model. And then we used this predicted demographics in the travel behavior model, which in our case was a trip generation mobile phone GSM records that gave us the trip rates. So we used this predicted demographic groups to explain the number of trips a person was making. And we got a set of estimated parameters. And so this was during the estimation phase. And then in the application phase, actually, we did not need the kind of CDR data anymore. Sorry, we did not need the GSM data anymore. We could directly infer the demographic features from the CDR data, and we use that as the input for the trip generation model, because from the known sample, we already knew what the predicted demographic group was. So we did some kind of holdout sample-based testing to see like what was the performance of the demographic prediction model, and it was quite kind of good in a sense that they had a good match with the actual observed demographics. And we also compared the improvements in the trip generation model, where what we got from the observed demographics versus what we got from the predicted demographics in the sample where we knew the demographics. And we saw that there it was quite a similar performance between the two data sets as well. So it was quite a small subsample, but the results kind of served as a proof of concept that having the demographic features of a subsample of the users can be used for actually making these probabilistic predictions about the demographic groups, which can be used for travel behavior model. And we use the trip generation in this case, but it can be applied for other travel behavior models or actually other urban applications as well. Like for instance, like when we're interested about behavior during disruptions or other type of non-traditional travel behavior models, this can be useful as well. So, and this can be particularly useful in countries where the survey data is not reliable and the passive data sources are kind of the only sources of data. So just in terms of the conclusions, so the case studies and some of the other follow-up or related work that I have done, it kind of demonstrates that the passive data can be still be used to uncover the similarities between the different user groups. And they can be used for developing predictive travel behavior models with anonymous data sets. And they can be applied in different urban choice contexts, like residential location choice or evacuation, etc. So any questions?
Great. Thank you very much. That's perfectly on time. In fact, even 5 minutes ahead of schedule, which is great because that gives us a bit more space and time for discussion. Do we have any questions on the from the audience? I can see there's one more question, but I think it was for the previous speaker. Feel free to drop the question in the Q&A, and if that for whatever reason doesn't work, it should, but you know, the gods of Zoom don't always cooperate. You can drop it on the chat, and I'm monitoring both. In the meantime, I had one question, Therese Majid. You talked, if I understood it correctly, when you opened the talk before you jumped on the examples, you said that one of the main challenges of using machine learning type of methods that it's hard to infer behavioral properties. And I was wondering, to what extent do you think, well, to what extent do you think that that's solvable, or is that a core property of machine learning, and then we just probably shouldn't spend much time on these. And also, to what extent do you think there are other areas in transport behavior or in transport geography where you think there's a lot of potential for machine learning?
Actually, maybe it was not clear. What I was meaning is not that machine learning is not capturing the heterogeneity. Rather, what I was saying is actually, we did some work with students as well, like comparing the performance of machine learning and econometric methods in different scenarios. So we found that if the kind of training scenario and the prediction scenario is quite similar, in that case, just simple machine learning models have a good fit. But if we are looking at so one study we did was we had data from 2005 and 2010, and we were comparing the performance of machine learning model. And there it did not perform very well because maybe the behavior has changed quite a lot. So that's where I was referring that we need to actually go via the influencing factors more carefully so that even if the demographic group has changed, we can still make predictions. So because maybe the causal relationships are still stable,
yeah,
but the differences in behavior are originating from the fact that the user group is now different.
And then that would not be necessarily
Yes. So for
something great
example,
for machine learning. Yeah.
yes, but so for instance, machine learning can still be combined with the econometric models, and that's something I'm working on as part of my UKRI Future Leader Fellowship, where, for example, in this case, the machine learning models can be used for maybe looking at clustering the users instead of having a kind of a traditional econometric model or traditional probabilistic model. And then that can be linked with an econometric model. So usually these disciplines do not most of the work has focused on the comparison, but there's a lot of potential in, I think, combining. And actually, that's another thing that we are doing in Turing with Professor Ed Manley. I have formed a special interest group in Turing, which is on bridging machine learning and choice modeling, where we are actually we are going to have the first event on 8th November, which will be on transport, where we will hear about people working on combining machine learning and econometric models in the context of transport. But it's not about only transport, other like health and marketing, there it's applicable as well. Because I think the choice models or the econometric models are traditionally developed using for small data, and for passive data we can benefit by combining these with machine learning. So I think that answers your second question, that
yeah.
I think
Excellent. Thanks
we
very
can get
much,
the
and
best of both worlds.
feel free also to drop the link to for the audience to know where they can read more about the workshop and sign up. Any more questions? No. I might ask, since we do have time, and I think there was a lot of really interesting food for thought in the talk. Whether I do have one more question, and it was more a comment or asking you to comment a little bit on your experiences in blending. If I'm correct, one of the two examples at least combined mobility data with CDRs and with other sources. What in your experience has been the main challenges in bringing all of these data sets together, where you have data about similar populations, but you can't necessarily link one data set to another one directly?
Okay, that's an interesting question, because in the two case studies I presented, we did not have to do that, because for the subsample, it was the same people for whom we had the call detail and GSM. But actually, the same PhD student, his fourth paper was on kind of combining survey data and mobile phone data. So there, what he did was actually, so he had a sample from a survey, but the mobile phone data was from a different group of users. So there, what he did was a bit of so he developed the initial models based on the survey data, but then he did some aggregate level of readjustment in the model parameters so that it better matches the trip rates from the mobile phone data. So we could not do a one-to-one connection, but we use the mobile phone data as more of a kind of ground truth to some extent, because the survey data was just like about 1,000 users, where the mobile phone data was about 90 million users.
Yeah.
So we use the mobile phone data to recalibrate the survey, the model we got from the survey data. So maybe I will share the link to that paper in the chat box as well.
Yeah, I think that would be super useful. Okay, and then we have one from actually one of the panelists. One of the panelists who couldn't post on the Q&A. That's one of the beauties of Zoom. Let me see if I can dig it out. Yes, the question is, so based on your experience, is it possible to predict geodemographic information without a pre-labeled sample? And Krasen, if you can post on the chat, maybe if you want to unpack that a little bit more, or jump on the chat, on the voice.
Right, yeah. So my question is that, based on your experience, thanks for the talk, first of all, what is the geographic information that's easiest to attach to mobility data and to this type of secondary data?
I think it's difficult to give a definitive answer because it depends a lot on the city. So I guess in some cities, the income may be possible to infer even without label data, if the city is quite segregated in terms of like where rich people live and where kind of people with lower income live. In that case, maybe the unlabeled data is enough. But when we are talking about kind of more like gender, for instance, or age or employment status, these type of things, I think at least like my experience so far is we need a small sample of labeled data. Otherwise, it becomes quite extremely challenging task to predict the demographics.
Super. Well, great. Thank you very much, Charisma. And then we're moving to our next speaker, and Francisco, who's managing that one. Thank you.